Have you ever wondered how machines learn to classify, predict, or even make decisions? Today, we're deep diving into the fascinating world of neural networks. But wait, we're doing it all from scratch. And today, what I want to share with you is about optimization. So having all those lessons we have discussed and learned in the past, we are now going to have a more exciting thing. No pre-built
Wow!
libraries, no shortcuts, just raw Python and pure logic. If you're ready to get your hands dirty, stick around because we're building and training a neural network step by step. Neural networks are the backbone of many AI applications inspired by how the human brain works. They process information through interconnected layers of neurons. So each neuron in our network takes an input, processes it, and passes it on the next layer. In our code, the dense layer class is where we define these operations. So we had that one before. This one shows the dense layer class and it shows how it is done. So weights are initialized with small random values and biases are set to 0. These act as the starting points for the network's learning process. So now that we understand the architecture, let's talk about how data flows through these layers. Alright, let's break this one into different layers. So to create a neural network, we need three main components. We have the dense layers here, then we have the activation layer. So in our activation layer, we have two ReLU activation, and we also have the softmax activation. So dense layers, these are fully connected layers where each neuron is linked to every input. So think of it as the foundation of our network. This one shows it, and if you want more discussions about dense layer, you can go back to our discussion about dense layer. We have a separate video for that. Then we have activation functions, wherein we have two, as what I've said. So these introduce non-linearity, enabling the network to learn from complex data. So in our code, ReLU filters out negative values. And then the softmax function, this one, converts the output into probabilities. This means that ReLU is implemented by taking the maximum of 0 on the input value. This ensures that only positive signals are passed forward. For more information about the ReLU activation and the softmax activation functions, we have a lessons on that. So you can just go back, and then when you're done with it, you can just come back to this video and then learn more about how optimization is done. Then after these two layers, now we have the next one, which is the loss function. So loss function, this part, helps us measure how well the network's predictions align with the reality. In a way, you are getting how big or how small the number is. So when it is too big, the
Wow.
absolute value is too big, then there would be more loss. That means it's too far from the reality. If it's
Oh
small, then it's too close to
yeah!
the reality. Categorical cross entropy calculates. Now we are in this part. Again, categorical cross-entropy calculates the difference between predicted probabilities and actual targets. This loss guides the model to improve over time. So here's what the magic lies, or here's where the magic lies. Let's walk through the implementation step by step. So we will go back to this one first so that we will be having a deeper understanding about different layers in the processes. So first, here in our code, we define our layers, our dense layer to be more specific. So notice how we initialize the weights and biases. So these small random values are the starting point for learning. Then we have the past or the forward method here, which is inside the dense layer function or the class dense layer. So this is the function forward that calculates the weighted sum of inputs plus biases, passing the result to the next layer. Now the result is passed to this layer, the class activation. The first one is the ReLU activation, to be more specific. So here we implement the ReLU. It's simple yet powerful for handling nonlinear data. And then finally, the result of this one is passed to the next activation function, which is the softmax activation. We use softmax to convert the outputs into probabilities, especially useful for classification tasks. So once our model is built, it's time to train it. So we start by first generating our synthetic data. So again, we use NFS here. So this data simulates the real world scenarios for our network to learn from. So now let's focus on the training loop here. Here's what happens during each iteration. So the input data flows through the layers, this one. So you can see the layer 1, layer 2, layer 3. As you could see, we defined which one is layer 1, the layer 2, and the layer 2. But how exactly the input data flows through the layers? At each stage, weights and biases are updated to reduce the loss. But how exactly do we measure the loss? This is where the categorical cross-entropy loss functions become essential. But anyway, let me first execute this one so we could see what's happening and what the results would be. Now let's execute this one. Okay, now let me continue with my discussion before we execute this and find what the results would be. So again, this is where the categorical cross-entropy loss function becomes essential. Then let's break it down. So the first step is clipping the predictions to avoid numerical instability. So this ensures we don't encounter issues with extremely small or large numbers. Next, we calculate the confidence level for the correct predictions. So either from the categorical labels or from one-hot encoded vectors. So by applying the negative logarithm to these confidence levels, we penalize incorrect predictions more heavily. So this encourages the network to improve in subsequent iteration. So let's first execute this one. Now we can see the results. Let's look at the results of our training process. So initially, the value or the loss value starts high around 1.0988 with an accuracy of only 33.33%. So this is expected because the model is untrained. So as we progress, even small improvements in loss values, such as reducing it to 1.0936 at iteration 19, this one, let me highlight it. Alright, lead to a significant increase in accuracy, jumping to 66.67%. So by iteration 75, let's look at that. Let me highlight this. Alright, by iteration 75, the accuracy reaches 67.00% with a loss of only 0.9726% or 0.9726. This iterative improvement demonstrates how the network adjusts its weights to minimize errors. At iteration 156, accuracy peaks at 87% with a loss of 0.7236. Let's go to that. Iteration 156. Where are you? 15. This one. Alright. So later iterations such as 321. Where is 321? Show a stable accuracy of 91.33% with a loss of 0.3583. And this indicates convergence. So here's the kicker. If a particular weight adjustment doesn't reduce the loss, we simply revert to the previous best state. This keeps our model from getting worse. After thousands of iterations, we achieve a well-trained model. Let's check its performance. So accuracy measures how often the model's predictions match the actual target. By the end of training, the loss stabilizes around 0.1728 and the accuracy hits an impressive 93.00 or 0.9300 or in percentage 93.00%. Every step from initializing weights to training the network is now crystal clear. Neural networks might seem complex, but as you've seen, breaking them down into smaller steps makes them manageable. Whether you are building an AI model or just exploring, there's so much you can create. Thanks for watching. Don't forget to like, subscribe, and drop a comment with your favorite part of this video. Until next time, keep coding and keep innovating.